Video, we are starting section 10.1, and our objective is to find arc length and convert degrees into radians. So we've dealt with measures of arcs, but now we'll actually find their length, and we've dealt with degrees, and we kind of saw that radians was coming, and now we're ready to learn about that. So before we start, let's go ahead and look at our warm-up. Just to kind of review, we need to find the indicated angle or arc. So number one wants us to find angle INM. So INM is a central angle. And as we look at this, we're seeing we've probably got a diameter MJ going through the center there, which would mean that our angle INM would need to be 100 to make 180 with that diameter. So angle INM is 100 degrees. Number two, angle or arc, KLI. So we've got to go all the way around here. So we need to look at a couple things. One thing I'm noticing, we've probably got a couple of diameters here going through the center. And anytime I have a diameter, I know I have 180. So I know from H to K is 180. So if I can find H to I, then I'll have my whole arc. Well, let's see if we can find the rest of these. I see 115, which looks vertical to these two angles combined. And if I already know that this angle and arc are 45, then I should be able to subtract from 115 and find that missing arc. So 115 minus 45 should be 70. So that missing arc and angle there would be 70 degrees, which means from H to K, again, is a diameter, so we'd have an arc of 180, that semicircle. So if we subtract those two arcs of 70 and 45, we get our arc HI is 65. And now we're ready to add that to our 180 to get our entire arc of 65. So let's see, 180 plus 65, that should be 245, I believe, 245 degrees. Okay, number three, the measure of angle WYU. So we're looking for this entire angle here. I know a piece of it because I see arc WV, which would mean this part of my angle is 51. So if I could find this arc, or that angle, I guess, but either one of them, then I can find my whole angle that I'm looking for. So I'm just going to kind of think about what I do know. I see other arcs and their central angles that I do know, which means the only thing I don't know is that one arc. So I can just subtract from 360 all of those arcs that I have. So 360 minus 51 minus 90 minus 114 minus 45, and we get 60 degrees. Oh, whoops, I didn't do that right. That should be, let me try that again. 360 minus 51 minus 95, excuse me on that one, minus 114 minus 45. There we go. So 55 degrees would be that missing angle in there. So to add those two together, we'd get 106. So our missing angle would be 106. All right, let's go down below the warm-up. It says, recall that the measure of an arc is the same as the measure of the central angle that intercepts it, which is what we were just using as part of our warm-up. The measure of the arc is in degrees, which we've been doing, while the arc length is a fraction of the circumference. Now, when we talk about arc length, we're talking about if we were to put like a piece of string on a curved arc and then maybe pull it straight along a ruler to see how long it was. I want to know the actual length. So we're going to think about that as a fraction of a circumference, because circumference is the length around the circle. So our last little sentence here says, thus, the measure of an arc is not the same as the arc length. So we've been using arc measures with degrees, and now we need to find arc length. So we've got a picture here. We've got our radii marked. We've got our central angle. which is still going to be the same measure over here, but now with a lowercase l, we're going to talk about length. So depending on how small or how big our circles are, our lengths are going to change because our circumference will change. So we need to figure out some proportions that are going to help us do this. So let's look below. It says, consider the following to help us figure out arc length. So all circles are similar, and we looked at a proof of that in Unit 9, and therefore two circles can be dilated so that it is mapped on top of, circle 2 can be dilated so it's mapped on top of circle 1. So if we took circle 2 and made it bigger, it would be identical to circle 1. We could also go the same way, or the same thing going from circle 1 to circle 2. The same dilation maps the slice of a small piece to the slice of a large piece. So if we just look at that slice of circle 2, we could map it to that slice from circle 1. So since our corresponding lengths of similar figures are proportional, which we've talked a lot about, then we can set up the following relationship. So from circle 1, we can take radius 1, and then from circle 2, radius 2. So we have a proportion of radii and then lengths. So we have our arc length from our circle 1 and our arc length from our circle 2. So we can make this proportion. And then we can solve for any piece of it that we want to, but our goal is to be able to find length. So we're going to solve for L1. So we do some cross multiplying. So I've got the work down here. So if we take our diagonals, R1 times L2, and then we take our other diagonal, L1 times R2. And then if we're solving for length 1, we'd have to divide both sides by R2. So this is going to give us our proportion. We're taking L1. To find L1, we need to take length 2, so from our second circle, divided by R2, the radius from our second circle, and we can multiply that to our radius from our first circle. So it says below, this means that the arc length of L1 is equal to the radius, R1, times some number. So this is going to be kind of our sum number we've got to figure out. What is L2 divided by R2? And it says we can find that number by looking at how the central angle compares to the entire circle. So for example, if we have a central angle that is 30 degrees, when we compare it to the whole circle, we'd get 30 over 360, which does simplify to 1/12 of the entire circle. So 30 degrees is 1/12 of the entire circle. The arc length, the length of the arc that is intercepted by the central angle of 30 degrees would also have to be 1/12 of the circumference. So if our central angle is 1/12 of the circle, then our arc length must also be 1/12 of the circumference. And as just a reminder, I put it right here below. To find circumference, we take 2 times pi times r. So therefore, we can set up some proportions here. We're going to compare our central angle. So let's label here a little bit. Theta is our central angle. So we need to compare our central angle to our entire circle, that 360 degrees for that circle. And then that's going to be equal to our L, which is our arc length. And we're going to compare that to our circumference. So here's our two ratios creating our proportion. So let's go ahead and solve for L. So if we cross multiply, we get L times 360, and I'm going to go ahead and write that 360 before the variable L, is equal to theta times 2 pi r. And then we need to divide both sides by 360. We're trying to isolate our L. So if we want to find the length of an arc, it says that we have pi times 2, theta times 2 times pi times r divided by 360. So I'm going to go ahead and think about simplifying this because 2 and 360 can simplify. And that's going to leave us with just our theta and our pi in the numerator over 180. And I'm going to write that radius out front. This right here is what we were looking for up here when it said L2 divided by R2. There's our two things that we need to know to find our length. So I put this in our box here. Note in the equation, so in our equation that we've solved from above, the number of L2 compared to R2 is this ratio right here. So this is really important to us. This is how we're going to find the length of an arc. So let's go ahead and turn our notes to the second page and let's try some. So at the top of this page, just kind of nice and organized here, we've got our arc, our formula for finding arc length. So it says if the central angle of a circle with radius r is in degrees, then the length, or L, of the arc it intercepts is given by. So we have our nice formula we just came up with from the other side. So example 1 wants us to draw the representation of each arc length and then find the length of each arc. And we're going to round, it says, to the nearest thousandths. So we should be able to, from what we've done with our unit circle and stuff, be able to do a pretty good estimate drawing of where these thetas are. So in example A, we're trying to estimate where 72 degrees is. So we know that would be in the first quadrant. We know where 90 is, so we're just going to estimate the best we can about where that 72 degrees would be. So this would be my 72 degree central angle, and I'd like to find the length of its intercepted arc, L. So according to my formula, length is equal to pi times my theta, so 72, divided by 180, and we're going to multiply that to our radius, which is 5 in this case. So we're definitely going to be using a calculator, and we're going to round to the nearest thousand. So that's 3 decimal places. So I'm going to pull back up my calculator here. I'm going to go ahead and type in a fraction. We've got pi, so our second caret button, times 72. I'll go ahead and just use my parenthesis. And we're dividing that by 180. Whoops, not 480. 180. And then we'd like to multiply that to our radius 5. And we're going to use 3 decimal places. Be careful if you need to round. We've got 6.283, so 1 is not big enough to round that up. So actually, I'm going to change my equals to an about because we're rounding here. 6.283, and we're going to make sure we put our units if they're given to us. This one is in centimeters. So for this particular circle, the length would be about 6.283 centimeters. Let's try it again on problem B. 120 degrees would be into our second quadrant, just a little bit past our 90. So there's our arc, our central angle, which means we're trying to find the arc that's across from it. So to find the measure of that length of that arc, I need to take pi times my theta divided by 180 and multiply that to our radius. So our length, I'm going to go ahead and just start with my about because I'm probably never going to get a whole number because pi is in there. And I'm going to go to my calculator again and I'm going to type that in. And I'm going to do an alpha y equals with that fraction in there and do a second pi or second caret to get my pi. So pi times 120 divided by 180. And we need to multiply that to our radius of 7. So 14.66, but that 7 is going to round that 0 to a 1. So 14.661, and that would be in inches. So not arc measure, but arc length. How long is this arc depending on its circumference? So let's move on to the radians that was in our objective. It says that another way to measure angles is with radians. The radian measure of a central angle is defined as the ratio of the arc length compared to the radius. So that's right there. When we think of radians now, we need to think of this ratio. Arc length, which we now know is represented with L, as compared to the radius. So we get a new Greek letter right here. It says if, and this is, if you're not familiar, is alpha. It's a lowercase alpha. If alpha is the radian measure, so it's just standing for whatever degree it is, just like we have theta that represents things. This is just another representation. If alpha is the radian measure of a central angle, then we need to be able to make this proportion. So we're making a ratio to find our radians, and it says length, arc length, compared to radius. Well, we just found out that the formula for finding arc length is pi times theta over 180 times our radius. So that right there is length, but then we're supposed to divide by the radius. And that means that if we simplify and we multiply by the reciprocal of that denominator, the r's will divide out, which leaves us with this conversion right here, where theta is the measure of the central angle in degrees. So to convert any angle in degrees to radian measure, we just have to multiply the angle in degrees by pi over 180. So below we've just kind of got a nice laid out here. If I want to convert from degrees to radians, if I want to take any degrees and convert it to radians, I multiply by pi over 180. If I want to go backwards, just like we can in math, we would have to do the reciprocal of that. So if I start with a radian and I want to change it back to degrees, then I do 180 over pi and I multiply that. So we're going to get some practice converting right now. Let's go ahead and look at example 2. If we want to convert each degree into a radian measure, and notice the directions say to express radian measures in terms of pi. We don't want to approximate this. We're going to leave this in terms of pi when we talk about radians. So below we have 3 degrees, some of which maybe we recognize from our unit circle, maybe not. And I want to convert them into radians. So according to what we just went through, in order to take a degree and change it into radians, I have to multiply that degree by pi over 180. So I'm going to multiply this to pi over 180. Well, we know really this is over 1. So if we multiply this, we end up with 25 pi over 180. Now, I want to leave pi there, but I can simplify the coefficient in front of pi with my 180. So I'm pretty sure that that's at least divisible by 5. So if I'm not sure, let's see, 180 divided by 5 leaves me with 36, and 25 divided by 5 is also 5. So I feel pretty good about saying that this would simplify to 5 pi over 36. Let's try it again on B. 135 degrees, to change into radian measures, we would multiply pi over 180 to 135. So again, we're really doing multiplying the numerator to numerator and the denominator to denominator. And we're thinking, can this be simplified? So again, this is at least divisible by 5, maybe more. So maybe just because it's a little bigger numbers, I put it into my fraction if I want to. And I'm going to leave off my pi and see if that'll simplify for me. So that simplifies to 3/4, which means if I leave my pi with my numerator, I end up with 3 pi over 4. 3 pi over 4 is the radian measure for 135 degrees. Problem C, 50 degrees times pi over 180 would give me 50 pi over 180. And then I can simplify. And maybe I realize that it's divisible by 10, so I can just take, 50 divided by 10 is 5, and 180 divided by 10 is 18, and 5 over 18 doesn't simplify anymore. So that's going to stay the same. Let's go backwards. In example 3, if we already are given the radian measure, what is that in degrees? So this is just multiplying by that reciprocal. In a degree, I can't have a pi. So the nice thing that I'll notice when I start to multiply by that reciprocal and get 180 over pi, pi's are going to divide out every single time. We can't have a degree that has a pi in it. Pi's are saved for radians. So in this case, I end up with 180 over 2, which those divide out and leave me with just 90 degrees. So 90 degrees and pi over 2 are talking about that same measure. Let's try again on B. 180 over pi should convert this to degrees. So again, those pi's are going to simplify. So if you want, you could use your calculator a little bit more. We need to do 7 times 180, and then we'll be dividing that by 4. So this is 315 degrees. Is the same thing as 7 pi over 4. Okay, last one. 180 over pi will convert this radian to degrees. So again, our pi's will divide out. I'm going to go ahead and use my calculator. 5 times 180, and if we divide that by 3, we're going to get 300 degrees. So a 300 degree angle is the same as a 5 pi over 3 radian measure. All right, go ahead and self-assess. How do you feel about finding arc length and converting between degrees and radians? And good luck on your assignment.